Questions on the second assignment? Due Wednesday. I hope everyone started it already. All right, so let's go back to the lecture and we'll finish talking about 3 and 4, although we did started talking about 4, and then 3 is coming up here. So interpretations. Okay. Given an abstract predicate logic statement, okay, an interpretation of that statement, okay, is interpretation consists of a choice of domain and a choice of meanings for those predicates. Okay, so and an abstract predicate logic statement may be true in one interpretation while it's and false in another. And we've seen this already with stuff like problem number 2 here. Here's one statement, and then you look at it over several domains. Sometimes it's true, sometimes it's false, depending on what the domain is. So now just looking at this more formally, consider something like this one here. Here's an interpretation of that statement. So there's a statement. I didn't say what the domain is. I didn't say what H is. I didn't say what M is. I didn't say any of that stuff. Right? So let's give an interpretation. And we'll note that in this interpretation, it's false. Okay? So the domain is the positive integers, 1, 2, 3, 4, 5, 6. H of x is even, and M of x is x over 2 is an integer. Now, you'll notice that these are actually equivalent, right? Hx is true if and only if mx is true. Whatever, doesn't matter. That is an interpretation. Not that every interpretation has hx logically equivalent to mx. Okay, but in this interpretation it is. And when you take that interpretation, for every x, hx implies mx. So over the domain of positive integers, for every x, if x is even, then x over 2 is an integer. That's true. That's essentially what the definition of an integer is. Or sorry, definition of what even is. And there exists x in the domain such that x is even. That's true. So here, this is true, and this is true. So together, this conjunction here is true. Now, the statement is not a conjunction, it is an implication. Okay, the hypothesis is a conjunction, but the final connector is this. So in the conclusion here, for every x in the domain, x over 2 is an integer. That's false. Okay, so we have true implies false, so altogether the statement is false over this interpretation. Remember, given an implication, the only way to make it false is like this, for the hypothesis to be true and the conclusion to be false. And implication is false only when that the hypothesis is true and the conclusion is false. All right, can you think of another interpretation under which this statement is false? Now, we'll do one that's under which it's true also, but the more important one is coming up with interpretations where it's false. Why is that? Is because these tend to be sort of abstract notions of logic, and people are interested in when abstract notions of logic are just simply true. So showing that they're not just simply true over any interpretation involves finding an interpretation where it's false. Not that it could never be true. It certainly might, but that's not good enough. All right, so let's come up with another one. Let's leave the domain the same. Let's choose a different h, different x, or different h, different m. Leave the same domain. We need to make the hypothesis true. The hypothesis needs to be true, and the conclusion needs to be false. So this is another which the statement is false. So again, look at your domain. So this box is the domain, all the positive integers. And we want that for every x, hx implies mx. In other words, the x's which make h true are contained within the m's. The x's which make m true. So something like that. And where this is false, not everything is m. So m, essentially, any interpretation you come up with where m is properly contained within the domain, and properly contains h, or doesn't have to properly contain it, or it could be equal to h. So in the previous example, it was equal to h. Let's make an example where it's not actually equal. So anything looking like this, it's going to work, because this is going to be false, and these will both be true. All right, this D, domain D, that's all the integers. M is just some subset of those integers, positive integers, and H is some subset of the integers satisfying M. Come on. We can come up with one. Pick your favorite subset of the integers, besides the even ones. We did that already. Pick your favorite subset of the positive integers. You may make the example as cheesy as you like. The cheesy example, the cheesier the example, often the better. So you can explain to people, how ludicrous what they're saying actually is. It's so ludicrous, you don't even, account for the cheesy examples. You all must have some favorite subset of the integers besides the even ones. Or the odd ones. Let's not do that. We already did even odd. Think of something else. Oh, come on, guys.
We could do x as prime.
Ooh, prime, nice. I like that. Or m should be prime, I think. X is prime. Okay, so now some subset of primes. Are all primes odd?
No.
No, not all of them, right? X is an odd prime. Right, so for every x, h of x implies m of x. Is it true for every x in this domain, x is an odd prime, implies x is a prime? Let's
Yes.
even prime. X is an even prime implies x is a prime. That's true. Does there exist x in the domain such that x is an even prime? There's one.
2.
2. That's true. So true and true is true. For every x in the domain, x is prime. For every x in the domain, they're all prime.
It's false.
That's false. So overall, this statement is false. Interpretation number 3. This is number 2, sorry. This is number 2. Let's now do interpretation number 3. Copy all of this, actually. So I'll start it off. So m will be 18 is less than or equal to x is less than or equal to 22. So x is between 18 and 22. And then h of x, some subset of that. So m of x is all the x's between 18 and 22. So h of x, some subset of that. Guys, come on. Some subset of 18 to 22. X equals 20. So again, for every x in the domain, if x is equal to 20, then x is between 18 and 22 includes it. That's true. There exists an x in the domain such that x is equal to 20. Sure, it's 20. That's true. So the hypothesis is true. And for every x in the domain, x is between 18 and 22. That's false. So altogether, the implication is false. All right. So that was interpretation number 3. How about an interpretation under which it's true? Now, again, this is an implication statement, and making it true is a triviality. Making an implication statement true is a complete triviality, because all you need to do is what?
Make the hypothesis false.
Make the hypothesis false. And the hypothesis is a conjunction, so just make this part false. So, again, we'll just use the same domain. Doesn't really matter what the domain is, and make H so it doesn't matter what m of x is. Make h of x just something false that doesn't exist. Make h of x such that this is false. There exists something in the domain of positive integers that is h. Something that doesn't exist in here. H of x identifying something that doesn't exist in here. So x is a horse. Right? Don't care about this. I don't care about this. Don't care about this. This is false. So the hypothesis is false. The conclusion is whatever. So the whole thing is true. Sorry. I'm going to make it true. Right, with implications, making an implication true is easy to do because all you got to do is make the hypothesis false. Okay, and in this statement, it's even easier because the hypothesis is a conjunction. So all you need to do is make one of the things, one of the terms of the conjunction, and the hypothesis false. So the easier one is this. Right, make that false. So whatever and false is false. And false implies whatever is true. So that was interpretation number 4, where we made the statement true. So in general, it's more important to find interpretations where abstract statements are false rather than true. Important to find under which statements are false. The reason being is the following. Definition. So an abstract predicate logic statement is called valid. So this is the notion of like a tautology, although it's not called a tautology. It's said to be valid when it is true under any interpretation. An abstract predicate logic statement is valid when it is true under any interpretation. So, for example, something like what we were just looking at, so does anybody see what we might do to this statement to make it a valid one? Well, it's just a quantifier really that's messing stuff up here. Now, we're not going to get too deep into this, but just at least so we know the terminology here. So I can fix this by changing the for all here to there exists. Right? So when is an implication false? When is an implication false? An implication is false when the hypothesis is true and the conclusion is false. Well, this hypothesis is true when H is contained within M, this part. Right? So this is true as long as Hx is contained within Mx. Like we have in this picture here. This is true when something, right, satisfies H. When some X makes H of X true. And then because that thing that made H of X true is contained within M of X, so that same thing that satisfies H of X, that same X that satisfies H of X also satisfies M of X. Right? In order to make the hypothesis true, this needs to be true, H needs to be contained within M, and this needs to be true. Something is contained within H. But now, this is automatically true, because that something that was contained in H is also contained in M. Right? So, true implies false doesn't happen. So, this is a valid statement in predicate logic. Doesn't matter what the interpretation is, right? It's always going to be true. Just one example there, like a more complicated example than what we're going to be concerned with. The only one really we're concerned with is the following. And it's called De Morgan's laws for predicate logic. And they are the following. So, kind of what we've been saying for a while now. For every x, p of x, not true, right? Not all x are p. Not every x is p. Not every x is p by definition of what for every x means. So, not every x is p by definition. By definition is something isn't p. Something is not p. right? Not every horse is brown means there exists a horse that isn't brown. Right? Not every student takes Math 2800 means some students don't take Math 2800. Similarly, there is no x. There is no x satisfying p of x. By definition of there is no x which satisfies p. Means what?
All X don't satisfy P.
All x don't satisfy p. Right, so those are De Morgan's laws for predicate logic, and they're more or less by definition. Okay, why are they considered to be De Morgan's laws? Well, because universal quantification over a domain is essentially taking a big conjunction over everything in the domain using P. It's a conjunction of everything in the domain over P. Existential is a disjunction over everything in the domain for not P. Right, so like A and B and C and D and blah, blah, blah. Not, in propositional logic is not A or not B or not C or not D or so on and so forth. So a big conjunction, when you negate it, is a big disjunction of the negation of each term. And vice versa. Right, so that's De Morgan's law in propositional logic. And universal quantification is essentially that. Guys, give me just a moment. I'll be right back. All right, guys, sorry about that. So De Morgan's laws for predicate logic, and they're important when you want to write the negation of a English language statement which uses predicate logic. Are important for negating predicate logic statements written in English in either symbolic logic or just in English. Or French or Spanish or whatever else. So for now, in propositional logic, we were, when we were doing negations, what we did was we translated things from English to symbolic logic, then we negated them, and then translated them back into English. Right, so here's the solutions to assignment 1. Oops. What did I do? Oh, yeah, that's right. I put this on the first page. Oh, I forgot what these were. So the statement was A and B, right? The processor is fast and the printer is slow. The processor is fast and the printer is slow. So we wrote it as A and B, and then not A naught or B naught via De Morgan's law for propositional logic. And that is the printer is not fast or the processor is not fast or the printer is not slow. Right, so we went from symbolic logic to negate. We went from English to symbolic logic, negation, and then back to English. So here we kind of want to skip that middle step unless you absolutely have to use it. So here we like to skip the middle step of using, for English, we like to skip the middle step of using symbolic logic unless we really have to. So, for example, write the negation of each statement. I forgot which one I asked you about. Make sure I don't repeat that. Oh, so flowers in red. Okay, so all horses are brown. All horses are brown, negated. Well, this is a straight application of De Morgan's, right? All horses are brown means, some horses are what? Right? All horses are brown. So not all horses are brown is some horses are not brown. Right? So we don't negate the quantifier. We like to flip the quantifier when we're negating things. So not all horses are brown is some horses are not brown. Similarly, some horses are purple. So not some horse, well, I guess not some. So there is a horse that is purple. To say there is no horse that is purple means what? Right? There is a horse that is purple. Negated is there is no horse that is purple. There is no horse is negating the quantifier. We don't want to negate the quantifier. We want to flip the quantifier and negate the statement afterwards, just like how we have it written here. There is not a purple horse means every horse isn't purple. All horses run fast and eat grass. All horses, they run fast and they eat grass. So, negated, all horses become what?
Some horses.
Some horses, what? What about
don't run fast?
Some horses, what? So this is run fast and eat grass. Negate that and you get what?
Don't run fast or don't eat grass.
Yeah, either don't run fast or don't eat grass. How about something like this? Let's take a doubly quantified statement. Every bee likes some kind of flower. Every bee, right, so negated. So this is, right, every bee, for every bee, there exists a flower, right? And then forget about what's actually going on in here. Just write this. So I'm not going to call it that. I'm going to call it P. So for every B, there exists a Y. For every X, there exists a Y, PXY. And PXY is the bee likes the flower. X is a bee and it likes a flower. Whatever it is, I mean, it's all just incorporated into here. Every bee likes some kind of flower. Now we're going to negate it. De Morgan's law says to do what? What does De Morgan's law say? This is a universally quantified statement. Every bee does something. So when you negate it, it becomes there exists X such that this isn't true. So this is for every X, something. Negated is there exists an X, not something. But that not something is again quantified. So you apply De Morgan's law and you get what? There exists X such that
All Y, not
all
PX.
Y. Yeah, P not XY. Whatever.
Or P not XY. I mean,
Yeah. Doesn't like flowers. So every bee likes some kind of flower. Right? Every bee likes some kind of flower. Negated is going to be some bees what? Right? Every
Don't
bee.
like.
But yeah, sorry. Go ahead. I'm sorry. Yeah, right. That's it. So some bees don't like any flowers. Iconoclastic bees. Right? So every bee likes some kind of flower. No, that's not true. Some bees don't like any flowers at all. Those grumpy bees. Or if I said this, so every bee likes some kind of flower. Some bees like all flowers. Some bees like all flowers. So here we got some bees like all flowers. Let's see if I can fit this in. Some bees like all flowers. So now I want to negate that. So you flip the basically, De Morgan's saying flip the quantifiers. Flip both of them. So that means for every X, there exists a Y, P naught X, Y. However you got quantifiers stacked, flip them in that same order. So there exists an X for every Y, PXY. Negated is for every X, there is a Y, P naught XY. So some bees like all flowers. Negated is, well, all bees. All bees what?
Don't like some
Don't
flowers.
like some flower. You want to say it singularly, every, even though it's universal, you can say it singularly or plurally. Every, like all bees, that's a plural type statement. You're talking about, all bees in general, like all bees together, or every bee. Well, you're talking about like all bees again, but just one of those every bee, the archetypical bee. every bee has some flower he doesn't care for, or it doesn't care for, or doesn't like. How about this? This is a little trickier one. No, I don't think. Sort of a weird one. Make it too weird. No. Oh, sorry. No. What am I trying to say? That's already negated. The one. So I want to do a for every, for all, for all, for all. How can we say that? We had some example earlier. Come on now. Here it is. Okay, only bees like flowers. So only bees like flowers. So only bees like flowers. If it, from the work we did above, interpreting that into predicate logic, we saw that this was for every x and for every y. It was a universally quantified with both variables, pxy. So now let's not worry too much about what pxy's logical structure was, but it was universally quantified for both x and y. Only bees like flowers. Okay, so if we're going to negate it, what happens to those universal quantifiers? Right, just like what's been going on in these last two examples, right? If you had for every x there exists a y, negated becomes there exists an x for every y, p naught. There exists an x for every y, p becomes, for every x there exists a y, p naught. So now we've got, right, for every x and for every y, p becomes what?
There exists
There
X.
exists an x.
exists Y.
Yeah, p naught. Okay, again, let's not worry too much about what the logical structure of p naught is going to be, but it's going to be a doubly existential statement. So only bees like flowers. Negated is going to be what?
Some bees don't like some flowers.
Only bees. All right, so
Not all bees.
when you say not only bees like flowers, not only bees like flowers means, right, so only bees like flower mean nobody else does. It means I don't, you don't, hummingbirds don't. So not only bees would be someone.
And the bees.
Someone else likes flowers.
Someone else likes which? Right, this is only bees like flowers. Which flowers? All of them. So this is saying someone other than a bee likes which flower?
Some kind of flower.
Sorry?
Some kind of flower.
Some kind of flower, right. Somebody, or so someone other than a bee. So someone who is not a bee likes some kind of flower. Now, that's maybe a little awkward in when you write it in English. I think only bees like flowers. If you want to negate it, typically you just put not only bees like flowers. Not only bees like flowers. All right, how about, let's see, some other doubly quantified statements. I think we've covered most of it. Covered most types of examples. Let's look back here. Bees only like flowers. Bees only like flowers. Bees only like flowers. So that was again a universally quantified statement. Bees only like flowers. If it's a bee and the bee likes this thing, that thing is a flower. All right? If you say it as an if-then, to say it as an if-then statement, so if X is a bee who likes Y, then Y is a flower. Bees only like flowers. They don't like anything else. They don't like their hive. They don't like their queen. They don't like their fellow workers. They don't like honey. They don't like stinging people. Nothing. They just like flowers. Right? So that's like saying if it's a bee who likes Y, then Y is a flower. And it's universally quantified in X and Y. universally quantified. Universally quantified in X and Y. Because it's an implication statement, it has to be universally quantified in X and Y. So, if it's a bee that likes Y, then Y is a flower. So negate it, again, right, X and Y become existentially quantified. Existentially quantifying X, existentially quantifying Y, and then the implication, when you negate it, becomes what? When you negate an implication, it becomes what? It becomes a... It becomes a conjunction. All right, so we're out of time, so I'll just write it out. Is, right, there is a bee who likes something other than flowers. All right, bees like only flowers. Every bee and every Y that he likes is a flower. So now we've got some bee likes something that is not a flower. Okay, so that's all the time we've got today. Please get started on this, and let's have some questions on Monday, all right? Please get started on it this weekend. Look at these examples. Do the examples on your own. Then look at my solutions, and then, see where you went wrong or how you went right, and fix your mistakes, and then go on to the homework, and, let's get started on it. And when you get stuck, just send me some questions. If you want to email me questions, I do check my email on the weekends, okay? Alrighty. Have a good day, a good weekend, guys, and I'll see you on Monday.